Hey everyone, let's check out this nice example together. In this example, we have two currents. One is carried by a straight long wire, and the current value here is 6.28 amps. And another one carried by a loop. We don't know where it's heading, clockwise or counterclockwise. And this current could be going this way or this way. We don't know. And the idea here is to find the direction of the current in the loop in such a way that the net magnetic field at the center of the loop is equal to 0. Well, how is that going to happen? Okay, first of all, let's check out the magnetic field resulting from the long straight wire, which is tangent to the loop itself. According to the right-hand rule, number 2, this is the wire going this way to the right, and this is my again. So if you grab on it in such a way, your thumb points to the direction of the current in the wire, then the magnetic field coming from the wire at the center or anywhere above the wire is going to be coming out from the screen. So that's the magnetic field coming from this wire, anywhere above, but we care where it is directed at the center, which is above the wire, then the magnetic field is directed this way. So for the loop, we need to put the direction of the current so that it makes a magnetic field that must be pointing down. And why is that? Because that's the only way, if we add these two vector quantities, because magnetic field is a vector quantity, that's the only chance that they will both add up to 0. Why? Because that's what we're looking for. We need the net magnetic field at the center of the loop to be equal to 0. We need to find the direction and the value of this current in the loop. But let's try this one, the one that is going counterclockwise. If we actually put, I'm going to assume this is the loop, and if I am doing this to direct myself for the direction of the current because it's going this way, then the magnetic field is coming out. If it's coming out, that's not going to happen, so automatically we're not going to use this one. So that's not the right one. We are going to use this one as for the direction of the current in the loop. I'm going to call the current in the loop IL, and I'm going to call the current here in the straight wire IW, just to distinguish between the two. Alright, now we established that B at the center, B coming from the wire, and B coming from the loop must add up to 0, or we can say B from the loop as a value must equal to B in the wires as a value must be equal to B in the loop as a value. Okay, because we already established the direction already here. Okay, we don't have to worry about that anymore. All right, what is the magnetic field coming from the wire? It is mu naught I over 2 pi r. And what is the magnetic field coming from the loop? It is mu naught I over 2 times r. But remember, this loop has two loops, so we have to multiply this by 2. Okay, now 2 with 2 cancels, r with r cancels, mu naught with mu naught cancels, so we end up with this just simple equation: I over 2 pi must equal to I for the loop. So I should call this loop, and this should call this wire. This is the wire, and this is the loop. Okay, now we just need to plug in the numbers. I wire is equal to 6.28, so 6.28 divided by 2 pi must be equal to I of the loop. Now let's find the value of I of the loop. I of the loop is equal to, well, 6.28 divided by 2 pi is almost equal to 1, so I of the loop is equal to 1 amps. And that's it. So that's the direction of it, and that's the value of it, and we solved this problem. And that's it for this one. Thank you.